Okay, let us continue our discussion on diffusion. First, we will discuss one point, which is a redistribution of dopants at silicon dioxide interface. And that is a practical problem, because during your drive-in diffusion, along with the dopant atom, along with the diffusion of dopant atom, some oxide will be formed at the silicon dioxide. So when an oxide will form at the silicon surface, silicon dioxide will form, then automatically an interface will be created, which is known as silicon dioxide interface. Now, along with the drive-in process, if we don't grow silicon dioxide, then the problem is that the dopant atoms will evaporate from the surface, silicon surface. So in order to prevent the evaporation, in drive-in process, some oxide is also formed. So that means during drive-in, oxidizing species, that is oxygen or H2O vapor, is also inserted into the, is also flown into the diffusion tube. So there the impurity atom, which were already in silicon during pre-deposition time, those impurity atom will redistribute at the silicon dioxide interface. And here one term is important, which is known as segregation coefficient. Here is written segregation coefficient M is equal to impurity concentration in silicon divided by impurity concentration in silicon dioxide. That is the segregation coefficient. Now, here this is the silicon layer and this is the silicon dioxide layer, and this the dotted line is the interface. And in this particular curve, we have assumed that M is less than 1. M is less than 1 means segregation coefficient is less than 1. That means impurity concentration in silicon dioxide will be more compared to impurity concentration in silicon, because M is the ratio of impurity concentration in silicon divided by impurity concentration in silicon dioxide. Now, if M is less than 1, means impurity concentration in silicon dioxide will be more, and that is seen in this curve. This is the interface, and N by NB is plotted against X. X is the vertical distance from the surface, and N is the concentration at any point, and NB is the background concentration. Then N by NB is plotted across X. Then we will see in silicon dioxide the profile is like this, and in silicon dioxide and silicon it is like this. And at the interface, always we found that the doping concentration at the interface in the silicon side, dioxide side, is more compared to the doping concentration in the silicon side. And in both the curve, we found that dopant concentration in the oxide side is more compared to the doping concentration in the silicon side. And this two curve is for two different phenomena. One is slow diffusion, another is the fast diffusion. If the diffusivity of the dopant is slow, then it is known as slow diffusion. And here example is boron. So in case of boron, it is a slow diffusion and M is less than 1. So slow means from the silicon dioxide, the dopant atoms will evaporate at the from the surface to the ambient is very slow. You see, this is the surface, this x equal to 0 is here, is x equal to 0. So that means this is the silicon dioxide interface is here and surface is here, and this side is the environment, isn't it? Diffusion environment. Now here the slow diffusion in silicon dioxide, the dopant atom will evaporate into the ambient. So that's why here it will not be straight line like this. You see, it is not constant. Constant, that means this profile is not constant along x. So it is gradually decaying because the doping atoms are evaporating. Similarly, from here also the dopant atoms will go into the silicon dioxide in the drive-in diffusion process. And all the time, since m is less than 1, this point will be at higher and this is at the lower n by nb, the higher n by nb. But if the diffusion is a fast, example is the boron with hydrogen. In presence of hydrogen, if boron diffusion takes place, so this is a fast diffusion. And there also m is less than 1. If the diffusion is a fast, then what will happen? You see, that means more evaporation. This is silicon dioxide and this is the ambient. In the ambient, the dopant atoms will evaporate at a faster rate, and so that it will try to reach in the zero level. And since here the decaying fast, so from the bulk silicon, the dopant atom will also enter into silicon dioxide at a faster rate. So here also, if you compare this curve with this, here you see decaying rate is sharp, rapidly decaying, because it is a fast diffusion. Because of the fast diffusion, evaporation is more, and because of the more evaporation from the silicon dioxide into the ambient, so the dopant supply from the bulk is at a faster rate, and so the curve here is a decaying nature at the surface. But this point always keep at a higher level compared to this point, because m is less than 1. M is less than 1 means impurity concentration in silicon dioxide will be more compared to that in silicon. That is also reflected here. Okay. Now, this is one case for m is less than 1. But when m is greater than 1, then the case is different. This two curve shows when m is greater than 1. So when m is greater than 1, is impurity concentration in silicon will be more compared to impurity concentration in silicon dioxide. So this is impurity concentration in silicon, which will be more compared to that in silicon dioxide, which is less. And here again there are two phenomena. One is slow diffusion, other is the fast diffusion. Slow diffusion, m is greater than 1, example is phosphorus. Fast diffusion, m is greater than 1, example is gallium. And here you see how the impurity atom redistribute during the drive-in process, where the silicon dioxide is also formed at the same time. The redistribution of impurity and impurity atom goes deeper into the silicon bulk. Now here in this curve is a slow diffusion. That means the impurity from silicon dioxide will evaporate into the ambient at a slower rate. That means the curve is something like that. And this point is a lower level compared to this. This is because of m is greater than 1. This m is greater than 1 means in silicon it will be high. At the time silicon it is always high compared to this point. But slow diffusion, that means this profile of this curve will be something like this. Only at the surface slowly it diffuses into the ambient, that is known as evaporation, loss of impurity atom. Okay. Similarly, in the other curve we found in different shape of the profile. Here fast diffusion, and example is the gallium, whose m is greater than 1, segregation coefficient is greater than 1, at the same time it is a fast diffusion. And because of that we found that this portion of the curve at the interface, that means at the surface of silicon dioxide, is almost 0, because diffusing fast, evaporation is fast here, so it is bending like that. Okay. Similarly, here also this from the bulk silicon, dopant atoms will come at the silicon dioxide from the bulk. So here loss is at a faster rate into the ambient. Similarly, supply will be more. So that's why this point curve is something like this. The faster incorporation into from silicon to silicon dioxide, and again from silicon dioxide to the ambient. Ambient is here. This is a 0 surface. This point is the surface. Here is the Si-SiO2 interface. And in both the curve, you can see at the interface, dopant concentration in the silicon side is more. Here also it is more compared to silicon dioxide. Here also it is more compared to the silicon dioxide side. That means M is greater than 1 for slow diffusion, and the fast diffusion, the profile takes different shape. This is the example of phosphorus, and because of M is greater than 1, at the interface always, that means at the surface, phosphorus try to accumulate more, and that also you have seen in your this anomalous diffusion profile of the phosphorus, because a flat near the surface, if you now after that if you remove the silicon dioxide, because you can etch silicon dioxide completely after driving, then you can see the profile of the dopant atom in the silicon. Then this part will not be there, it is only this part, and if you see this part, so at the surface there is a lot of accumulation, and after that it will gradually fall like this. So here is the flat surface, it will accumulate near, then some king, and then something like this. Okay, it will at a larger depth it will fall like that. Okay, this is the redistribution of impurity atom during the drive-in diffusion process, and diffusion profile takes different shape. This is all regarding the profiles. Now we will discuss something on the evaluation of the diffuse layer. You have done the diffusion, then after diffusion is completed, then you have to go for evaluation of the diffuse layer. What do you mean by the evaluation? For evaluation, we mean basically two parameters. One is what is the junction depth and what is the sheet resistance or the resistivity of the diffuse layer. One is the junction depth and the second is the sheet resistance or resistivity of the diffuse layer. And sheet resistance or resistivity will give you an idea of how much dopant atom has been incorporated, has been diffused into the diffused layer. Okay, the sheet resistance or resistivity of silicon will give you an idea of how much dopant atom have been incorporated into the silicon crystal. If the incorporation of dopant atoms are more and more, so then obviously the resistivity of that particular layer will be higher or lower? It will be lower. Resistivity, conductivity will be more, this resistivity will be lower. So that will give you an idea, and from there some relations are available. You can, if you know the junction depth, you can easily calculate what is the value of the doping concentration, peak average doping concentration of that particular layer. So those two parameters will help you regarding evaluation of the diffuse layer. And there are two methods of junction depth measurement. One method is known as angle lap and staining. Angle lap and staining is a method by which you can roughly estimate the junction depth. Accurate measurement is very difficult in this particular technique. Some other techniques are available, I will discuss later on, but here you can roughly find the junction depth of the diffuse layer, and that method is known as angle lap and staining. And here in the diagram you can see a diffuse layer is the red region and the blue color is say background in substrate, and red is the diffuse layer. Now we want to find the width of this red layer, which is the diffused portion. How can you do it? So first you have to lap. Lap means you can have using some polishing powder in one side, if you rub it, so it will form a shape like this. Okay, Now invert it and you lap it in one corner at a small angle, then you will take the shape like this. Okay, and that angle of lapping should be very low. It is within 1 to 5 degree only. So after lapping, it will take this shape of the wafer will take this shape. And now if the theta is the angle which is within 1 to 5 degree and T is the thickness of the red region, so easily you can measure this distance from here to here, which is the diffused layer. Now if you can measure the D distance using microscope cursor, then the tan theta is equal to T by D, tan of theta is equal to T by D, and from where you can get T equal to D tan theta. If theta is very small, so you can assume here theta, that means T equal to D theta, so that will give you the T. Now the point is that how do you define the region D, and that definition is obtained by staining. This is the second is a staining. You have to use certain solution. If you put few drops of that solution, color of that particular diffused layer will change. The color changes, you see here it is a blackish green. If the color changes, so under microscope you can easily see what is the distance D, and if you can measure the distance D, easily you can find the T, which is the junction depth. So this is one technique which is known as angle lap and staining, and the detailed methods are shown here. Angle lapping is done using some abrasive powder, and that abrasive powders are carbonundum, alumina, boron carbide, etc. And these granules or powders are of size 100 to 200 mesh per grit. This is one unit of the granule size of this particular powder. And now after abrasion, then you can get the shape which I have shown in last diagram, and after that in the diffused region you can put 100 a stain solution, and that stain solution, there are two types of stain solution available. One is known as P stain, another is known as N stain. And in the P stain means P layer the color will change, and N stain means diffused N layer color will change, and that changing of color will take place if the doping concentration of that particular layer exceeds certain value. Otherwise it will not, it is sensitive to the doping concentration. And P stain solution is formed by using 100 cc of concentration hydrofluoric acid of 49% and few drops of HNO3, almost 0.1%. That means if you mix this solution, which is known as stain solution, and this solution you put few drop on that lapped portion, and then you keep the sample for 1 or 2 minutes in high intensity lamp. Inside it, say you can use a 100-watt table lamp, and under this lamp you keep the sample for 1 to 2 minutes, and you will find that diffused region in the lap portion, that color will change, and P diffused layer becomes black because of formation of SiH4, H2SiF6 and SiO. SiO2 silicon dioxide, but silicon dioxide will not form, it will form SiO monoxide. So because of formation of SiO, H2SiF6, the color of that diffused layer will change, where you put the stain solution, and after putting the stain solution you have to keep the sample under high intensity lamp for 1 to 2 minutes. Similarly, you can change the color of N layer by using a stain solution, and that stain solution is formed by 200 grams of copper sulfate and 1 liter of H2 plus 10 cc HF. This solution you mix it is known as N stain solution, and in N layer color will change if you use this one. Okay, so this is the angle lap and stain. Another method of angle lap and stain is a commercial method, because you see if you lap manually it is a time consuming. At the same time, you cannot get very nice lapping profile if 1 to 2 degree. In industrial environment, they use they lap in different way. What they do, they use a cylinder, and using some motor speed they rotate the cylinder, so that is a, and then a groove is formed in the diffuse layer. Here this is a substrate and this is a dope layer, and this is rotating, grinding wheel. Okay, if the wheel is rotated, so automatically a groove will form, and its radius of curvature is similar to the radius of curvature of the grinding wheel. A cylinder is used to group the wafer. A doping sensitive etch then removes the part of the top layer. Here you see doping sensitive etch, it removes the top of the layer, top of the diffuse layer. The junction depth can be found from the known diameter and the measured width of the lower abraded group. Now you can see easily this portion. Now you can find the width of this group. If you find a relations are available from which relates the radius of curvature of this particular grinding wheel and this depth, if you find, then you can easily find the junction depth of that diffuse layer. So that is another version of angle lap and staining method. Okay, so these in this way you can get an approximate value of the junction depth of the diffuse layer. Okay, after getting the idea of the junction depth, which is xj, then we will see the resistivity value or seed resistance. So before going to the seed resistance measurement, another technique I will discuss, that is the interference method, is the Tolanski's method. There what is normally done, here you see in the lapped silicon, here we don't stain it. I mean, in this portion we never put any staining solution. Rather what we do, a optical flat layer is put on the top of this, the lap portion, then you irradiate with a monochromatic light, which is sodium lamp 5896 angstrom is its wavelength. If you irradiate, so here you see in this particular region an wedge will be formed, and here you will see the interference pattern. This is known as Tolanski's interference technique. So now the fringe pattern gives a direct measure of the vertical depth in wavelengths of illuminating source. If you know the wavelength of the illuminating source, here if you use sodium lamp, then its wavelength is 5896. Then if you measure the fringes, how many fringes are there, if you count it, then from that if you multiply it by 0.29, because you see this is divided by 2, lambda by 2, 0.29 micron, then you will get the vertical depth roughly. Tolanski's interference technique is easier than staining, but again the accuracy is not up to the mark. So if you see the interference fringes here by putting an optical flat, then you see how many fringe patterns are there in this particular region, and then easily you can get it by multiplying lambda by 2 approximately, then you will have the idea of the depth of diffusion. .29 micron is for sodium. If your light source is different, then obviously your thing will be different. This 29 value will change. Now in the side diagram here you can see how this lapping is formed, that is shown here. You see the red is a basically holder, cylindrical hollow cylinder is kept fixed, and the blue is another bulk metal, and on this bulk metal piece which is also cylindrical, and this can move inside this fixed hollow cylinder. This is a hollow cylinder, is the red, the cross section view, and this is the solid cylinder. And the solid cylinder, one edge is done like that, some edge, and that angle here is 1 to 5 degree, and your diffused wafer is fixed with the help of some wax or something like that at this particular edge. Now you rotate it. If you rotate, and this is the fixed plate, and in this particular plate you put the abrasive powder and water, then you rotate like this. Then here you see it will be the abraded, this particular portion, and you will get this sort of thing. The lapping is done, and you will get the shape of the slice is like this. Now if you want to go for staining, you put some staining solution. If you want to go for the interference method, just you put a optical flat slice here, and you will see the interference fringe pattern, and you can easily measure the thickness of the diffuse layer, junction layer. So now the seed resistance. A simple technique to obtain information about the impurity profile in semiconductor is the measurement of seed resistance. And seed resistance is measured by 4-point probe method. Here this is a diffuse layer, silicon layer, and 4 probes are used which are collinear, and there in the outer probes you send a current I and measure the voltage at the inner probes. Now the seed resistance is given by V by I into a correction factor, and this correction factor depends on the probe spacing, okay, as well as the dimension of the wafer. This will decide the correction factor. 4-point probes, that means 4 collinear probes are touched on the surface diffuse layer of silicon. A current is sent to the outer probes, and voltage is measured across the inner probes. You take the ratio of V by I, and that ratio V by I multiplied by correction factor will give you the seed resistance, which is known as RS, seed resistance of the particular layer. Seed resistance RS is defined by this relation, that is 1 by integral 0 to xj q mu nx dx. Integral 0 to xj q mu nx dx is the seed conductance, and 1 by seed conductance is the seed resistance. Nx is the doping profile. Nx dx 0 to xj will give you the total dopant, and if you have the average doping value, then you can multiply q and mu effective, you will get the conductivity. Reciprocal of that means, you see, to the power -1 here it is written, and you will get the seed resistance. And seed resistance multiplied by xj will give you the resistivity, and 1 by resistivity will give you the conductivity. Okay. Now you see, first you measure the junction depth. If you know the junction depth, then you go for measurement of the seed resistance using the 4-point probe method. If you know the seed resistance, RS is known, XJ is known, then what you will get? You will get the resistivity. So if you know the resistivity, 1 by resistivity is the conductivity. So if you know the conductivity, and that conductivity is equal to NQ mu. Mu is the effective mobility, and mobility of silicon at room temperature is known. Okay, mobility of electron or hole, if it is N type, then mobility of electron you have to consider. If it is a P type, mobility of hole you have to consider. So that is known value. Now if the mobility is known, Q is the electronic charge, so easily you can have the doping level. Average doping level at the surface, you can have nx value, n value. Okay. In this way, you can easily found the impurity concentration, average impurity concentration of the diffuse layer. So for that, you have to first measure xj, then you have to measure rs. So multiply these two, you will get rho, which is resistivity. Take the reciprocal, you will get the conductivity, and conductivity is the nq mu. So mu is the effective mobility, q is the electronic charge, and n is the concentration. Okay, concentration you can get easily. Now the 4-point resistivity meter, resistivity measurement, the techniques are this, already I explained. Current I is passed between two outer probes and voltage V is measured across the inner pair, and RS is given by V by I multiplied by correction factor, which is CF. The correction factor depends on probe geometry, a ratio of probe spacing to thickness of diffusion. For collinear probes, where probe spacing is much larger than the junction depth, the correction factor is 4.5325 approximately. It has been found if the probe spacing is small compared to the dimension of the wafer, the wafer diameter is large compared to this probe spacing, there is a parameter which is known as S by D. S is the probe spacing and D is the wafer diameter. Okay. So for that the constant factor also changes, and also when probe spacing is much larger than the junction depth, probe spacing in the range of say millimeter, few millimeter, and junction depth is of the order of few micron. So here probe spacing is large compared to the junction depth. So there the constant factor is 4.53. Normally V by I, what we get, we multiply it by 4.5325 and we will get the RS value, seed resistance value. Okay. So this is 4-point resistance method. Now measurement of impurity profile. There are two techniques by which you can accurately measure the impurity profile. One technique is known as SIMS technique, that is secondary ion mass spectroscopy. A typical SIMS arrangement is shown in this diagram. SIMS is secondary ion mass spectroscopy. What is done here, you see, sample is kept here, this is a wafer, this is a sample, and ion source and mass filter are used, and from ion source ions are ejected and those ions passes through the mass filter. The job of the mass filter is select a particular ions of specific mass. The rest of the ions are rejected here. Those specific ions are accelerated using some accelerating grids. These are accelerating grids, and those accelerated ions are bombarded on the surface of the wafer. The sample is bombarded by high energy ions and it will sputter some of the materials from the wafer surface because of the high energy bombardments. And the sputtered ejected material which are coming out from the wafer are passed through a mass analyzer. That means those secondary ions are analyzed with the help of mass spectrometer, mass SPEC, mass spectrometer. So spectroscopic analysis of the secondary ions are done in this particular module, and you can find how many amount of ions are there and how much amount of ions are there, and at the same time what are the different types of ions are there in the secondary ion beam. Depending on the impurities at the silicon surface, the secondary ions will be ejected along with silicon. Silicon will come out. Along with silicon, some those impurity atoms also will come, and those impurity atoms and ions are analyzed, mass analyzed, because silicon has got certain mass and arsenic different mass, phosphorus different mass, boron different mass, like that. So after mass analysis, it is sent to a detector, and the output of the detector is amplified and the signal is observed. Okay, and this is the basic diagram of basic schematic simple diagram of the SIMS. So it basically seems a heavy instrument, a highly complicated instrument, and it's not so simple if you look into the SIMS machine. And all these operations are done at very high vacuum of the order of 10 to the minus 10 millimeter of mercury. So a big vacuum chamber is required, and for acceleration you need a high electric field in the range of kilovolt, several hundred or thousands of kilovolt. So that supply will be there. Then the bombarded materials are analyzed, the secondary ions are ejected and these are analyzed. Mass analyzer is highly expensive. Okay, so the total thing which instrument which is described very simply using some block diagram is actually it is not so simple. And now the few points is written here. Energetic ions strike the surface of the sample where they destroy the crystal lattice, is a destructive phenomenon. The accelerated ions after striking the surface is destroy, damage the crystal lattice and eject material by sputtering. Striking energy is 1 to 5 keV. A fraction of ejected material is ionized. Those ionized ejected materials are collected and accelerated towards a mass spectrometer. Ejected material is ionized, they are collected and accelerated towards a mass spectrometer. Sputter rate can be increased and the concentration of several impurities can be measured as a function of depth. Sputter rate increase means every layer you are changing, because by changing the acceleration energy of the ions, so if acceleration energy is less, so it will eject material from the surface. If acceleration energy is more, these accelerated ions go deeper into the surface, and from there the materials will be ejected. So depending on the energy of acceleration, the secondary ions will come from deeper and deeper layer of the silicon. And if you analyze those ejected material, that means secondary ions, in the mass spectrometer, then you can have an idea how many ions are there. You can have a count. The secondary ions which are coming from the surface, how many atoms are arsenic, how many are boron, or how many are silicon atom, all you can analyze using this mass spectrometer. So if you count those atoms, and from there you can have an idea of per cc cubic centimeter that can be converted from the count. Okay, so this SIMS analysis has got certain disadvantage also. The problems of SIMS is it takes a larger time, because layer by layer you are taking or ejecting and then again you are analyzing. It requires a high vacuum. Vacuum level is of the 10 to the minus 9 torr. It is highly expensive, destructive. The test is destructive test. That means after sputtering you are disturbing the crystal surface, and the same cannot be used for further processing for fabrication of devices. Okay, same wafer you cannot use it. So once you test it, you have to throw it away. So it is a destructive phenomenon. So that is expensive, destructive. Samples thicker than 1 micron may take 4 to 8 hours to profile. That means thicker samples is using the SIMS technique, measurement of profile is highly expensive. Abrupt interface is difficult to measure, particularly if they are buried. These are the problems of the SIMS. In spite of all those problems, SIMS is nevertheless a powerful and widely used tool for profile measurement. Although it is complicated, although it is expensive and is a destructive diagnostic tool, even then it is widely used for getting an idea of doping profile. At the same time, what are the impurity atoms? This is very important, because in our earlier case you have some idea about the dopant. You know, if I diffuse phosphorus, we can say it is a phosphorus. If you diffuse boron, we can say it is boron. But other than boron as phosphorus, desired impurity, some non-desired impurity may go into the silicon. Those non-desired impurity may heavy metals, they may be alkali atoms, they will come from the furnace tube, they will come from other processing steps. So those impurity atoms, how do you know? Those the idea of those impurity atoms, that means undesired impurity atoms, can be obtained from SIMS analysis, because the ejected atoms, secondary ions, whatever is coming, those will be analyzed. If it is a different from phosphorus, that also it will show. We are diffusing phosphorus, for example. Along with phosphorus, what are the other dopant atoms incorporated there? That idea also you can get from SIMS analysis, which is never achieved in other technique which we have done this profiling, like spreading resistance measurement or 4-point resistivity and junction depth measurement. We can have the concentration value, some idea, but different impurity atoms idea we will not get on those diagnostic techniques. So another technique is also used in profile measurement, that is known as Rutherford backscattering technique, which is known as RBS. And RBS is again one involved process, is not very simple technique. And there in RBS system, high energy helium ion are used, helium ion source. Those helium ions are first filtered in a mass analyzer, and that particular mass analyzer helps you to separate helium ions from others. So those helium ions are accelerated to accelerating grid, and they are incident normally on the silicon wafer, the normal incidence. And after normal incidence, here the secondary ions will be ejected, and those secondary ions are analyzed in an energy analyzer, and the signal is amplified, and it is from the amplified signal we can have the counts. So in RBS, the energy of the backscatter helium ions can be used to determine the depth profile of the chemical composition of the wafer. That is the purpose of RBS. And here the salient points are like this. In RBS process, helium ions with energies in excess of 1 MeV are incident on the sample at near normal incidence, and the ions penetrate deeply into the sample. Impurities will backscatter the ions with a characteristic energy that depends on the mass of the impurity and its depth into the crystal. You see here, the backscattered ions will depend the characteristics of the backscatter ion will depend on the mass of the impurity and the depth into the crystal, silicon crystal. So by analyzing the backscatter ion, you will have idea of the mass of the impurity atom and its depth from the surface of the crystal. The backscattered helium ions are collected and energy analyzed, and from the energy analysis indirectly you can have the idea of the doping profile of the impurity atoms into silicon. The raw data from RBS system consists of counts versus energy. Okay. Now let's see what are its advantages and disadvantages. So the problems of RBS are: 1, backscattered signal from an impurity atom must be larger than the signal from the host material atom for a reasonable sensitivity of RBS measurement. RBS technique is limited to high mass impurities such as antimony and arsenic. Light mass impurities, it gives lot of error. As RBS technique does not require a sputter erosion of the sample to be measured, RBS is quick and non-destructive. This is the advantages of RBS over SIMS. However, its sensitivity is less than SIMS. So these 4 points are comparison with SIMS. So this is not a destructive process, because you are not using the sputter etching of the sample. You are just hitting the surface by a high energy helium ion, and you are backscattered. The helium ions are backscattered, and the backscattered helium ion energies are analyzed. The energy of the backscattered helium ion depends on the mass of the ion as well as the mass of the ion as well as the depth of the ions. So in this way, you can use RBS method for measuring the profile. Okay, let me stop here. Here we discussed most of the evaluation process of diffused silicon layer, diagnostic tools. Okay, thank you.